All right, there are a lot of pieces to this puzzle we're going to do today. I'll talk about the pieces individually, and then we'll put everything together. Okay? Um, if I had an x to the fourth equation, what are the possible roots, the possible rational roots? So plus or minus 1, 2, 3, 4, and 24. Does everybody understand that? Everybody's good there. How do you tell if one works? If you want to know if x equals 1, add up all the coefficients and see if you get a 0. How do you tell if negative 1 works? Switch the second sign and not the third, but switch the fourth, but not the fifth, and so on. And then add them together and you get 0, it works. Okay? What if there is a 6 out front? Then I need to extend this, and the factors of 6 are 1, 2, 3, and 6. So I have to divide all of those by 2, except for the ones that simplify. So 1 over 2 I need to do, but 2 over 2 simplifies, so I don't need that one. Because it's all of the factors of 6. Yes, so everything divided by 1, that's the original list, and everything divided by 2, and everything divided by 3, and everything divided by 6. But you can skip anything that simplifies. Because if it simplifies, it's guaranteed to either be in the list already or it will be in the list later. Okay? So we would do 1 over 2, 3 over 2, and that's it. And then I would move over to 1 over 3, 2 over 3. I don't need to do the 3. 4 over 3, 6 I don't need, 8 over 3. And then move on to the 6, 1 over 6, and then everything else simplifies. So that would be the list. Okay? That is called the rational root theorem. The rational root theorem says the possible rational roots are all of the factors of the constant divided by all of the factors of the leading coefficient. Okay? But that will only tell me rational roots. What does it mean to be rational? A fraction. Okay? But there are 3 types of zeros. You have rationals, which cover like whole numbers and fractions, and irrational roots. What do irrational roots look like? They have a square root in them. Okay? Or the third version would be imaginary. They have eyes. So an irrational root would be something like this. X equals the square root of 5. But if you have one irrational root, you actually have 2. So if one of them is the square root of 5, what's the other one? Negative square root of 5. And if I had x equals 2 plus the square root of 3, what would the other root look like? 2 minus the square root of 3. The irrational roots always come in pairs. Now, that's if every coefficient is a whole number. Right? See how my coefficients are 6, 2, 3, 2, and 24? If your coefficients have the square root of 8 or pi or some nasty number, then the roots could be lots of different things. But if all of your coefficients are whole numbers, then your irrational roots will always look like this. They always come in conjugate pairs. If you have root 3, you also have negative root 3. The same is true with imaginary roots. If my root was 2i, it comes with a partner that would be negative 2i. And if my root was 4 minus 3i, then 4 plus 3i is also a root. Does that make sense? So imaginary roots always come in conjugate pairs. Conjugates are the exact same thing with a different sign in the middle. Both the irrational roots and the imaginary roots come in conjugate pairs every single time. Okay, well, um, let's say we have an x to the third equation. I don't know what it is. And I try x equals 2, and I do the synthetic division, and I end up with a 0. What does that mean? That means x equals 2 is one of the roots, and x minus 2 is one of the factors. If I end up with x squared plus 6x plus, oh, let's make it big, 12, can I factor that? Are there factors of 12 that add to be 6? So 1 and 12 doesn't work, 2 and 6 doesn't work, 3 and 4 doesn't work. So if it doesn't factor, what does that tell me? The remaining roots are either irrational, which means they have square roots in them, or they're imaginary. How do we find irrational and imaginary roots? The quadratic formula. Negative b plus or minus the square root of b squared minus 4ac over 2a. Let's plug this in. 6 plus or minus the square root of 36, and then negative 4 times 1 times 12 is negative 48 over 2. 6 plus or minus the square root of negative 12. So the negative is going to come out and be an I. What about the 12? 2 root 3. Does everybody understand that? I went really fast. You good? Reagan? Okay. So 6 plus or minus 2I root 3 over 2. Now, I check, does this number, and this number have anything in common? A 2. You don't touch the inside of the square root. If we had the square root of 6 over 2, you cannot simplify that because it's not really 6. It's the square root of 6, which does not cancel 2. We end up with 3 plus or minus I. Those are the imaginary roots. Oh, sorry. Here I'm saying you can't cancel it, and then I forget to write it. So 3 plus or minus I root 3. All right? What if I had this? Does that factor? No. So we use the quadratic formula. 6 plus or minus the square root of 36 minus 8 over, well, why don't we, let's do one with the leading coefficient just for fun. So it'd be minus 4 times 2 is 8 times 3 is 24 over 6. So I get 6 plus or minus the square root of 12 over 6. And once again, 12 is just 2, 2, and 3. Pull out a 2. 6 plus or minus 2 root 3 over 6. Nope. I can still take out a 2. Take a 2 out of all of those. 3 plus or minus root 3 over 3. Is everybody okay with that? All right. So today we're going to be finding imaginary roots. So first, you have to look at the polynomial and see how many roots it has. How do you tell how many roots a polynomial has? It's the exponent on the leading coefficient term. Okay? So you find out how many it has. And then you look at the possible rational roots. You don't necessarily need to write them all down. Okay, but you know what the possible rational roots are. And then you start doing synthetic division to eliminate roots and find which roots work. What's the best way to make a guess on a rational root? Graph it. And usually you can get a good idea on the graph. Sometimes it might look like 3, but it's actually the square root of 10, which is really close to 3. So sometimes the graph can be a little misleading, but your best guesses will come from the graph. Okay? But there's one more thing you need to know, and it is called Descartes' rule of signs. Descartes looked at a lot of polynomials and he figured out a way to tell how many times the graph hits the positive x-axis and how many times the graph hits the negative x-axis. And it's called Descartes' rule of signs, and it's not hard to do. So let's say I had 2x to the 5th minus 6x to the 4th plus 2x squared minus, oh, I missed one. Doesn't really matter, but minus 5x squared plus x minus 1. Really? Did I really do that? Okay. So this graph can hit the x-axis 5 times. Does it have to hit 5 times? No, it might hit it 4 or 3 or 2 or 1, and it can't hit it 0. Why can it not hit 0? Because it's an odd number, right? And an even number is going to look like this, and an odd number is going to look like this. Does that one have to hit the x-axis? No. Does this one have to hit the x-axis? At least once. Okay. So what Descartes figured out, and you guys know Descartes, he's really famous for 2 other things. He's the guy who came up with the Cartesian plane, the XY graph. He invented that. And he was also an existential philosopher, and he came up with the phrase, I think, therefore I am. He and his friends were sitting around saying, well, how do you know you really exist? How do I know that I didn't create this entire universe in my own head, and I don't really exist, but none of you exist. I'm just a consciousness who has created this world for my own benefit. Uh-oh, that's freaking her out. So his answer to his friends was, and it was in Latin, I don't speak Latin, I think, therefore I am. That was his proof. I think, therefore I am. So did you hear about when Descartes walked into a bar? He sat down at the bar and the bartender said, hey, Descartes, would you like a drink? And he said, I think not. And then he disappeared. Okay, that was lame. All right, here is Descartes' rule of signs. You just read the equation from left to right, and it has to be in order. You have to have your x to the 5th, and then your 4th and 3rd, all the way down to the end. You count how many times the signs change. So our first sign is positive. Did the sign change from here to here? Yes. Did the sign change from here to here? Yes. Did it change from here to here? No. From here to here? No. From here to here? Yes. Okay? And you count up the yeses, and we have 3. And you make this chart positive, negative, and complex. If you count the sign changes, that tells you how many positive roots there are. So this has 3 positive roots. Okay? And then you go through and you change the sign on all of the odd exponents. So I'm going to go through, and every time the exponent is odd, I'm going to flip the sign. Every time the exponent is even, I'm going to keep the sign. So this one changes, this one stays, this one changes, this one stays, this one changes, and this one stays. So if you'll notice, I changed the 1 and the 3 and the 5, and everything else stayed the same. So you just write all of the signs out, but if the exponent is odd, write the opposite sign. So the x to the fifth gets changed from plus to minus. The x to the fourth doesn't change at all. The x to the third changes from plus to minus, and the x to the fifth stays, or x squared stays, and the x to the zero, nope, that's a 1. The x to the first flips, and this one is x to the 0, it doesn't change. Now I recount my sign changes. Did it change there? No. No. Oops, sorry, there. Yes. Yes. No. So there are 2 negative sign changes. Well, 3 plus 2 is 5, which is exactly what I expected, right? 3 positives and 3 negatives. So here's what the graph looks like. It's going to look something like this, right? We end up with 3 positives and 2 negatives. Okay? But does it have to hit 5 times? No. In fact, you might end up with something like this. Oh, I need to draw it in a different color. Right? Now how many positives does it have? It has 1 positive and 2 negatives. Where are the other 2? They're right here. They're imaginary. Okay? And you can see that as you move the graph up and down. Now it has, that's kind of a bad graph, but so now it has 1 positive and no negatives. Now it has 3 positives and no negatives. And now it has 2 positives and 2 negatives and 1 positive. And right there, it has 2 negatives and 3 positives. So you can always substitute 3 pluses for 3 imaginary. 3 positives, or sorry, not 3, that was really bad of me. 2 positives for 2 imaginaries. Because we know that the imaginary roots come in pairs. If you have 5i, you also have negative 5i. So you can change this 3 to a 1. And then those 2 that used to be in the 3 are now over here. Okay, now this seems really hard, but it's actually super easy. We could change these to complex, 0 and 2. Can you think of another combination? So how about 1, 0, what would that be? 4. It needs to add up to 5. Okay. What about this? 2, 2, 1. Can that happen? No, why not? You have to have 2 complex. Okay. What about 2, 1, 2? No. It doesn't work that way. The only way it will work is if you take 2 of these and substitute it for 2 of those. Or 2 of these and substitute it for 2 of these. You can't take 1 from each column. That won't happen, ever. So basically, if this number is odd, then all of those numbers are odd. If this number is even, then all of those numbers are even. Does that make sense? And then this column will always be even every single time. All right? So let's look at okay. All right. Let's count the sign changes. Is that? So I have a yes there, a yes there, and a yes there. Does it matter that I'm missing an x to the third? No. All that matters is that it's written in order. So my positives are 3. Can I go ahead and put 1 right there? No, because sometimes it doesn't work that way. Negatives. How do I find the negatives? I change every one that has an odd exponent. So does this one get flipped? Nope. Does this one get flipped? Nope. Does this one get flipped? Yes. Does this one get flipped? No. And now I recount, and I only have 1 yes. So 3, 1, 0. Because it's x to the 0. You never flip the constant. Okay? So 3, 1, 0 is one possibility. What would another possibility be? 1, 1, 2. What would another possibility be? There aren't any. Because remember, if this number is odd, then every number in that column has to be odd. And this number is odd. All of the rest of them have to be odd. Why don't I do 1, 3, 0? Wouldn't that work? Why not? That's why. Do you want to close that door? Once you count the roots, or once you count the positives and the negatives, you can never go up from that number. So I ended up with 1 negative sign change. Right? The positive sign changes, I got 3. The negative sign changes, I got 1. You can never go up. You can only go down. And when you go down, you have to go down by 2s. Okay? So what if I had 5 and 4? How big is this polynomial? This is an x to the 9th. Okay, so what's another possibility? 3, 4, 2, and I would keep them in order. I would do all of the 4s first in the negative column. So 5, 4, 0, 3, 4, 2, 1, 4, 4. Does everybody understand that? Now I would switch to a 2 in the middle. 5, 2, 2, or 3, 2, 2, or 1, 2, 4. Or wait, 5, nope, sorry. This should be 4 and this should be 6. Okay, are there any more? Yes. 5, 0, 4, right? We did all of the 4s and we did all of the 2s. Now we need to do all of the 0s. So 5, 0, 4 or 3, 0, 6 or 1, 0, 8. Okay, does that make sense? So this is called Descartes' rule of signs. You count the positive sign changes, you flip all the odd exponents, and you recount the negative sign changes, and then you create a table, and you come up with all of the possible roots. All right? Why would we do this? Well, it helps us with our guesses. So, let's say we had all right. Let's say I had x to the 4th plus 5x to the 3rd minus 7x squared minus 29x plus 30. Let's take all the information we know here. First off, What are the possible rational roots? X could be plus or minus 1, 2, 6, 10, 15, and 30. Everybody understand that? Let's count the sign changes. 1, 2 positives. So 2 positives. And then we flip all of the ones that have an odd exponent. So this one stays, that one flips, this one stays, this one flips, and this one stays. And then I recount 1, 2. So 2, 2, and 0. What else could happen? 0, 0, 2, 2, or 2, 0, 2, or 0, 0, 4. Okay. So does 1 work? 1 plus 5 is 6. 6 minus 7 is negative 1. Negative 1 minus 29 is negative 30. And 30 plus 30 is 0. So I know that x equals 1 and x minus 1 is a factor. Okay, so now let's use 1. I know it's going to work. 1, 5, negative 7, negative 29, and 30. Okay. I've simplified the equation, and I know that there is another positive root. How do I know there's another positive root? So up here, this row is out, and this row is out. So now, when I do guesses, do I want to do a negative number? Not yet, because I know that there is at least one more positive. Well, I know there's one more positive out there. Can I guarantee there's a negative root? No, it might be 2 negative roots, or it might be 0. So let's try 1 again. Does 1 work? No, 1 doesn't work. So let's try another positive number. 3, let's try 3. 3, 9, 27, 26, and that's way too big. Okay, so 3 didn't work. How about 2? Let's try 2. 2, 8, 16, negative 15, nope, positive 15, 30, 0. So I now know that x equals 2 is a root, and x minus 2 is a factor. Okay, does the remaining polynomial factor? So this is now an x squared plus x plus 15, x plus 5, and x minus 3, which gives me negative, or wait, they're both plus. So minus 3 and minus 5, x plus 3, and x plus 5. Does that make sense? Okay. What if I get down to the end and it doesn't factor? Then you have to use the quadratic formula. So all of those pieces are coming together now. The rational roots will tell you your best guesses. The Descartes rule of signs will give you an idea about positives and negatives. And in this case, we found one positive, so we knew that there was another positive. So that'll help you make guesses. So, how much time do we have left? Quite a bit, right? So this can be a little bit tricky, so I want to stretch this over 2 days. So we'll do a lot of the problems. Let's do 1 through um, we don't want to do 47. So let's do 1 through 46 all, or 3 through 46 all. So looking at number 3, how many positive roots does number 3 have? Now there are 3 roots, but how many positive sign changes are there? 0. How many negative sign changes are there? 1. So there's 1 negative root. And it's either going to be 1, 2, 4, 8, 16, 32, or 64. How do you find the best guess? Graph it. Graph it and then pick a number that way. And then don't forget when you do synthetic division with number 3, maybe we'll actually do that one. So on number 3, I'm going to try 2. And my coefficients will be 1, 0, 0, 0, 64. Wait, 3, 2, 1. That's too many zeros. 1, 2, 2, 4, 4, 8. That didn't work. So now what should I try? 3 does not go into 64. That's not an option. Let's try 4. 1, 4, 0, 16, or sorry, 4, 16. Oh, we want to do negative 4, right? So x equals negative 4 is one of the roots. And then I need to factor x squared minus 4x plus 16. Are there factors of 16 that add to be negative 4? Nope. So I need to use a quadratic formula. These roots are either imaginary or irrational. And it turns out they're actually imaginary. So 3 through 46 all. And we'll spend 2 days on this. If you look at... Oh, wait, we got another set we need to go over. If you look at 33 through 40, it says determine the possible number of positive real, negative real, and imaginary zeros. So all you need to do on 33 through 40 is the positive negative complex chart. Does that make sense? You don't need to find what the answers are. You're just building the chart. Okay. And then look at number 21. How do we create a polynomial when x equals negative 5, negative 1, and 2? Did we just do this in the last section? So x plus 5 times x plus 1 times x minus 2. And how do you multiply 3 together? You do the first 2 together and then get your answer and then bring in the last one. All right? Well, look at 23. X equals 3 and 4 plus I. What else must happen? The other one is going to be 4 minus I. So x minus 3 times what? X minus 4 minus I, that's this one. And the other one will be x minus 4 plus I. How do you multiply these 3 together? Do these first. Okay? And when you do, you're going to get this. Right. minus 4x plus 16 minus 4I minus, wait, one of those is a plus. This is a plus xi. This is minus xi, and then plus 4I minus I squared. What do you notice? The xi cancels the xi. The negative 4I cancels the 4I. What about negative I squared? Nope. I is equal to the square root of negative 1. So if I square both sides, I get I squared is equal to negative 1. So negative I squared is really just plus 1. What is negative 4I squared? It's really just plus 4. What is negative 9I squared? It's really just plus 9. So these are the numbers that you'll end up with over here depending on what i's you multiply together. And we learned last time we can skip all of the multiplication except the last one. We can skip all of the I multiplication except the last one. Okay? Right. So you can simplify it down to this times this, which is going to give you all of those. And then you have to do this one times this one, which will give you the last term. So you just do x minus 4 times x minus 4, all of those multiplications, and then you do the negative I times the I, which will always end up being positive every time. And it will always be like positive 4, positive 9, or positive 25. It will always be a perfect square. Because it will be like 9i times 9, negative 9i, which will be positive 81. Okay. Good luck.